Hey guys, it's Mr. Fernando, and today we're going to be going over basically all things so far we've covered with exponential functions. So things we're going to cover today that you might want to just skip through if you missed something or you want something in particular. We'll go over the equation, right? I'll go over how to get the equation from an exponential graph. I'll go over how to get the equation from just given information from a table. And then finally, we'll go over graphing or filling out a table when you're given an exponential function equation. You're given some data, and it's your job to end up graphing it, right? So we'll go in that order, right? So if you're trying to get to this part right here, you might want to skip to the second part of the video, right? First minute's gonna be me explaining the formula. So again, skip around to wherever you kind of need it. So exponential function, right? If you watch the video on geometric sequences, that was like a preview of a exponential function. Exponential function is something that looks like this right here, right? It's typically graphed, right? And it's a linear function where you input something and something gets outputted. But as you can see, right, it has a, oopsies, didn't mean for a highlighter. It has this aggressive curve, right, where it starts going slow and then boom, jumps up, right? It's different than a linear function or a linear equation that usually follows rise over run or slope. Linear functions are when it's just consistently going up or down in one specific constant rate. This has a curve to it, right? Now, our equation is built of three things, right? We have our, and I'm just gonna write it to the side without the highlighter. We have y is equal to a times b, with our b having a variable as our exponent. So what is our a? Our a inside of this equation is, if you think about geometric sequences, it's like the first number. It's the beginning or the root of your exponential function. And it's specifically, when you're looking to try to fill it out, wherever x is equal to 0, and whatever the output of that is, that's our a. So what do I mean by that? Well, let's look at this exponential function, right? So again, I'm gonna look to see if I can figure out what my a is. And my a, right, is where x is equal to 0. So this is my x and this is my y. Well, I'm looking for 0 right here, 0. And so on the graph, that would be this point right there. So I know that my a is 3 for a part of my equation. So I can actually start to fill this equation out. I have y is equal to 3 times, I need my b now, right? We'll go over what our b is in just a moment. Our b, this is what we call our common ratio, or what is the pattern that's being multiplied consistently every single time. So I'm going to show that in two ways. I'm going to show that on a graph, and then I'm going to go back to that, I'm on a table, and then I'm going to go back to that graph so you can kind of see what I mean by that. So I'm going to grab the b this time, right? Well, what color do I have my b? I bet it's blue. So my common ratio is what is being multiplied every single time, right? So when I'm looking at my outputs, do you kind of notice the pattern that's happening? I have a pattern that is going from 5 to 25, 25 to 125, 125 to 625. It's a consistent pattern that's being multiplied each time, or my common ratio of times 5, times 5, times 5, right? So in this one, I can see right now, my common ratio is times 5. So right here, I can actually also fill in the rest of this equation based off what I was told earlier, right? I know that my a is whenever x is equal to 0. So I have my 0 right there. Happens to also be 5. So this is a funny equation. Y is equal to 5 times 5 with a exponential variable as a your exponent. So I'm gonna go back over here, right? See if I can finish this one. So I'm gonna try to see what my pattern is, right? So this one's a little bit hard to think about, right? But if I'm thinking about my outputs or my y's, right? I have an output of 3. I see I have an output right here at the 1. I have 6, and then I have 12, and then I have 24, right? So if you think about it, right? How many just list out my numbers again? 3, 6, 12, 24, right? What's my pattern there? My common ratio that's being multiplied every single time would be I'm multiplying by 2. So in this one, what's happening is I'm starting at 3, or my 3 at 0 would be times 2 with an exponent of x, meaning that you can put in any number for x and you would get the corresponding output for your exponential function. So this is the equation right here. I have a finalized exponential formula. Now again, I'm going to go back to that original one with the table. Same thing, right? From a table, right, I gathered that my common ratio, I could see the pattern multiplying by 5. I got that because x is equal to 0, I can just put what my value of y is right there, and I can write my formula. So I'm going to do it again, both off a table and off a graph real quick. So let's do this one, right? So I'm gonna try to think to myself. I need 2 pieces of information for my formula. I need, well, when x is equal to 0, I'm looking at my table and I can see that, right? I can see that when x is equal to 0, my output is 18. So I know that this formula's first number is 18, or that's my A. My B, or my common ratio, is what's being multiplied each time. So look at this pattern. It's going from 8 to 6, 6 to 2, 2 to 2/3, right? Well, let me think what's being multiplied, right? What's being multiplied is, it's more like I'm dividing each time, right? I'm dividing by 3 every single time. But our formula uses multiplication, so let's think how else I can write that. If you wanted to, you can take this value and this value and you kind of put it like this, 6 over 18, right? And you could get yourself that's actually close to, or simplifies to, 1/3, right? And think about it, 1/3 is this, or multiplying by 1/3 is the same as dividing by 3. So 1/3 is our common ratio. So 1/3 with an exponential value, right? That's my B, that's my A, that's my exponential exponent as a variable, because you can put in any number for x. These are the tricky when you have division ones, right? So it's always a good thing to think to yourself that if this is the first y, and this is the second y, and this is the third y, and this is the fourth y, right? Like in order, right? If you ever want your common ratio, you're always able to do this even with more simple ones. Do y2 divided by y1. That's what I did, right? I took y2, 6, divided by 18, or my y1, and that got me 1/3, my common ratio. Going off this graph right here, right? See if I can do it again as well. So I'm looking for, again, where does x equal 0, and what is being multiplied every single time? Well, I'm going to look again and see that this is my x. That'd be right here, meaning 4, right? 4 is where x is equal to 0. So I have first number right here, 4, times, what's my b here? Let's see what my common ratio is. I can put intersection points. Let's see, there, here, here, right? Ooh, so that's the last little part's getting a little tricky, but let me try listing out those numbers again. When my input is -2, I have 16. When I have an input of -1, I'm spitting out the number 8. When I have an input of 0, I have the number 4. When I have an input of 1, I have the number 2. When I have an input of 2, I have 1. So what's my pattern here? Well, I'm dividing by 2, or I'm multiplying by 0.5 each time. 0.5, 0.5 is my common ratio. So my formula would be 4 times 0.5, and it's kind of already there, with an exponent of 0.5, right? So there you have it. That is filling out the formula from both either a graph or from a table, right? And these exponential functions, right, they tell you that you can put any value for x and it spits it out for you. And then because you're using exponents, you're multiplying each time, like there is that explosive growth. Like if you want to think to yourself, 2 to the first power, right? 2 to the first power would be 2 times 3 would give you 6, right? If you put in the number 2 for x, 2 to the power of 2, that's 2 times 2, 4. 4 times 3, whoop, 12, right? You're doing that every single step. Every single time you increase your x, you're increasing that times 2, times 2, times 2. So your number just keeps on growing. Alrighty, I'm gonna give a sec for people to kind of register what I'm looking at here, right? On this, I'm gonna kind of just cross this out for right now. We'll have a different video for this. We have a formula, right? I have given you guys an exponential function formula. This was a really bare bones one. We have one in just a second that's a little bit more complex, right? Or more similar to what we were just looking at. 3 times 2 to an exponent. And then this one is actually just with an exponent. If you really want to think about it, or you're like, wait, that doesn't follow the form, just put a little 1 right in front of it. There you go. 1 times 4 to the power of x. So here, you're like evaluating the function every single time, right? I have values for x that I'm going to put in and solve for. And I'm gonna see what I end up getting. So I'm gonna use my calculator. You might not be able to see what I'm doing, right? But I'm just gonna verbally talk it out. So I'm gonna be doing this function, again, like I just said. 4 to the x power. Well, I'm gonna then do on my calculator, 4 to the power of -3, and that gives me it's giving me a number 0.15625. I'm gonna round that. I'm gonna round that to let's say 0.2. And let me just do my next one. We have 4 to the -2 power. So 4 to the -2 power would give me, rounding again just a little bit, I'm gonna do that to 0.06. You might think to yourself, like, geez, that's really tiny numbers, but we'll see as I graph it what that looks like. I'm gonna keep going. 4 to the -1st power, that's gonna end up giving me 0.25. This next one, you can use a calculator, but think to yourself that anything ever to the power of 0 is always just 1. And then I already know what my 4 to the power of 1 is, just 4. 4 to the power of 2, 4 times 4, 16. And then 4 times 4 times 4, 64. So now I'm gonna try graphing this, right? It's just coordinate points, x and y. So -3, I'm gonna have, oh my goodness, just barely off the top of that, right? I'm going to x -3, and then I'm just going slightly above that. Probably inaccurate, but you have to really zoom in. So I have this one crossed out. I'm going to do a check mark next to it. Then I have -2.06, so -2.06. Again, probably a little off. -1 goes to 0.25. And then I have, at 0, I'm at 1. So again, I'd be somewhere around here. Maybe a little off. Check these off. At 1, I'd be at 4. At 2, I'd be at output of 16. So I'd be at right here. And look at that giant jump. And at 3, I'd be at 64, which is way off the graph all the way over here, right? So if I graphed my exponential function, man, look at that. It's just like what I was kind of looking at earlier, right? It has an explosive growth right here, because if you think about it to yourself, the pattern is I'm multiplying by roughly 4 every single time. Again, I rounded over here, so it's a little off, but if you look at it right here, times 4, times 4, times 4, times 4, right? So if you think about it, if I started right here, I'm at 1 times 4 gives me to 4. times 4 again gives you 16. And then times 4 again all the way to 64. And that's how these exponential functions work, right? That's why these exponents as a variable, or your variable as an exponent, really just explodes off the graph. So let's do just one last one. If you got the picture on this, probably just end the video there. But I'm just going to do one more, just because this one has an extra step. So, same idea. I'm going to do this part first. 2 to the power of -3 is my first input. I got 0.125, and then I'm multiplying by 3. So I'm going to multiply by 3, and I get 0.3. Let me do 3/8. I'm just rounding a bit again, forgive me. And then I'm going to have 2 to the power of -2, and that would give me 0.25. Now I have, let's see what, oh wait, times 3. I forgot to do the times 3 there. Times 3 would be 0.75. That's the best part about these graphs, is that you should be noticing the pattern that there should be a growth. There should be, especially if you graphed it, it should go in a specific pattern like that. So always check yourself with that. Now I have 2 to the power of -1, 0.5, times 3, almost did it again, 1.5. Now I'm just gonna use my exponent rules here, right? Anything to the power of 0 is 1. So 2 to the power of 0, 1, times 3, 3. 2 to the power of 1 is 2, times 3 is 6. And now you can do a couple things, right? You can keep using your calculator. You can keep inputting, right? Or maybe you start noticing, what's the common ratio? What's happening each time? 1.5 to 3, 3 to 6. Am I not multiplying by 2 every single time? Yeah, I am. 6 times 2 is 12. 12 times 2 is 24. Let's just double check that though, right? Let's make sure I'm not going crazy. Actually, in fact, maybe I did go a little crazy. Let's do 2 to the power of 2. 2 to the power of, whoopsies, of 2 is 4 times 3. Nope, that got me 12. And then 2 to the power of 3. 2 to the power of 3 is 8. 8 times 3, 24. So there's a big thing for you, right? Notice how it all connects, that you do have a common ratio that's multiplying each time, and it's just following this exponential function. If I graph this, it would look something similar to this again, where yet again, it's gonna be a graph that's just a little awkward. It's gonna grow a little bit quicker than the other one though. So like this one, I'm at 3. 1, I'd be at 6. At 2, I'm at 12. And then at 3, I'm at 24. So again, exponential function. All right, so that's what I got for you guys, right? Just give yourselves those reminders of how can you create your formula. Again, formula being just made up of two parts, or technically 3. Where is your value of y when x is 0? That's your first number. Your b is your common ratio, what's being multiplied every single time. And then your exponent, which is just your x values. Awesome. Have a good one, guys.